Hello, I am Andreas Ziller. I'm the author of the Debugging book, and I'm here to present you a new chapter. Okay. So this chapter is about asserting expectations. And this is actually one of the oldest techniques in debugging at all, which can be traced back to Alan Turing. You know Alan Turing, of course, the Turing Award, the Turing machine, founder of computer science, or one of the big founders of computer science, who actually invented or at least described this method for the first time in 1947. That is at the very, very beginning of the computing profession. And the idea of an assertion is to have the computer perform checks on the internal state of the program, as well as on any computation results while the program is executing. The idea here is that if you're working interactively, as with an interactive debugger, you step through the program and you look at the program state and you compare the program state with whatever you have in mind. And this, of course, well, this works, but it can be a rather tedious activity, in particular if you have to do this many times, or if you have to cover lots and lots of different variables and states. And it's actually precisely for such tedious and repeating activities that computers were invented in the first place, to actually do the work. So the idea is to have the computer do the checking for you while the program is executing. And since modern computers have millions of extra CPU cycles, they have no idea how to properly use them. So why not use them to check results? And since these results since this checking can be very extensive, you can check an individual condition for a long time, or you can also check lots and lots of conditions also in short time. It's a very, very efficient way to have the computer catch errors. And on top of that, the assertions, because that's the mechanism you use for writing such checks, actually can stay in your code, thus also help others to debug and help others to see what you actually had in mind or to understand your code. So what is this wonderful magical thing that does all of this? Typically, this is realized in a single construct. This is the so-called assert function or keyword, and assert, as we have it here. So this is assert in Python. Does nothing particular. It simply checks a condition, and if this condition is true, it continues as usual. So we have assert true. So here we go. I just did assert true. Nothing happens. It just simply evaluated true. We can also put in anything else that is true, say assert 2 plus 2 equals 4. There we go. This is also true. So if the condition evaluates to true, nothing happens. But if the condition evaluates to false, so if I write, for instance, 2 plus 2 equals 5, that's rather boring still, then what happens is that we get an assertion error. That is the statement raises an exception, and well, unless we do anything particular to catch this exception, this means that the program is terminated. And we also get information about the place where this happens, and we can also see the assertion. Actually, the assert can also, I can also say, I can also give an extra error message if I recall it right. So I could say 2 plus 2 equals 5. That's actually a quote from 1984. Winston. Oh, is it Winston? I'm not sure enough for that. So let's simply stick with 2 plus 2 equals 5, and you can say 2 plus 2 is 5, and we all love Big Brother. Here we go. For those of you who've read 1984, you will understand what this is, and you can see that the string that we actually add here as an error message is also reported in the failing assertion. But by default, we can simply say assert true, and then nothing happens. So what do we do with such assertions? The way we use such assertions is twofold. First, we use such assertions in tests. That is, for instance, to check whether a particular function yields the result that we want to have. So if we have, say, a square root function and we want to check that it works properly, then we can say, I want to assert that the result of this particular call equals this particular value. So square root of 4 is 2, square root of 9 is 3, and this should all work just properly. And we can also write our own assertion function in here. That's not too complicated. And assertions actually exist in all programming languages in some form or another. Sometimes it's a bit more complex. So for those of you who like to program in C or C++, in C or C++, assertions are implemented as macros, but they work just the same. So you can say, you can put in an assertion into your code, in this case with parentheses, this is C. And if you have such an assertion into your code and it fails, then you get a message that the assertion failed, together with diagnostics such as which function actually it is and where this assertion is. There's actually some magic behind that in order to find out where, in order to have a C program report something like that, which function of a particular call is in, as well as the text of the assertion. There's actually quite some magic behind it, and here I put some. I've put some definition as this commonly occurs in C programs. And if you always wanted to dig deep into C and C preprocessor programming, well, this is how you build assertions in C. The interesting thing here is, however, that this is conditional. That is, you can actually change the definition of the assertion from this big monster here, which actually prints out the error message and checks the error message, into this. And this is interesting because if you define this special variable here, and when compiling your code, then the assert command does nothing. So it turns into nothing, and that's an important thing. You can turn off assertions as you like, and that's actually also something you can do in Python. If you pass the -o flag to your Python interpreter, then all assertions will automatically be turned off. Why would one want to do that? Well, the reason is simple. With assertions, you can do lots and lots of checks, and these checks may be pretty time consuming, so you may wish to turn them off in production code, thus getting back the time that you previously spent on these checks, so your program will run faster, although at the same time you will have fewer checks than before, so you have to choose wisely which checks to activate and which one not. So let's make use of such assertions. So the first part here is where assertions are used besides testing. You can use them as assertions that are checked all the time. And these are used in particular in 3 different ways. First way is to check preconditions. Precondition meaning that you want to check whether the arguments to a function or to whatever process are actually valid and are as expected. We can stick with our square root function. Square roots is ideal for illustrating assertions. If you have a square root function, you may wish to place an assertion at the very beginning, and this checks that the precondition for the number x for which you want to compute the square root. You see, assert x is greater or equal to 0 because our square root function is not set to compute the square roots of negative numbers. Well, you can also do that. There's complex numbers in Python, but let's not go into that right now. And if you have such a thing, then you can go and you can invoke square root with -1. And then if you do that, you're going to get an assertion error. If you have, specifically for Python, you may also wish to check that x actually is an integer or a float. Remember, Python is dynamically typed, and therefore there's no type checking going on, which means that you can now also check that if you invoke square root with the wrong argument type, this will also be checked. So this is simple preconditions. These check whether arguments are correct. The more fun, however, comes in post conditions. These are assertions that check whether the value is correct, the computed value is correct. And for a square root function, for instance, if y is the square root that we just computed, then y squared should actually be equal to the value that we passed. And this is again something which we can place in an assertion. And the really nice thing is that once we do have that assertion in place, then every time that we invoke square root and we get a result back, then this result will be proven correct because it has actually passed the assertion. This is not a guarantee that square root will work under all circumstances. It can still fail, but at least then we get a notice when it fails. So if it computes and returns a value, this value will automatically be correct. By the way, although this is a classic example, y squared equals x, this only works in theory, this only works in mathematics, or if you do symbolic computation. In practice, you may have to go and do a closer check. In particular, because of rounding errors, you may wish to check that the difference between y squared and x is less than whatever small value you can come up with. Python provides a method math.isClose for that purpose, which apparently does the right thing and simply checks whether two values are close enough together to be considered equal under the limitations of Python computations. So now we can actually go and build a real implementation of square root. So we use a Newton-Raphson iteration here, which works and which actually provides us the correct square root. So with this implementation, if I do square root of 4, I get 2. That's right. But I can actually put any number in here, and any number I will put in here will automatically be verified at runtime, which is an absolutely great thing, because this means that whatever you put in there, all the results will automatically be checked, and you can now perfectly rely on this method. You cannot rely on this method to always produce a square root. I mean, it can still fail the check. And therefore, this may still not be the best. This may not be sufficient if you want to put the square root function into, say, a nuclear power plant or an aviation device or anything else that is critical. For this, you really want to prove that the square root function always does the right thing. So you need to do a fixed point iteration, need to do a fixed point iteration of the Newton-Raphson method. It involves some deep mathematical thinking. But if runtime verification is enough, if you can live with the fact that it occasionally may fail, then such runtime verification is just perfect. And then you can compute arbitrary square roots, and you can perfectly rely on this. So this is the main point of preconditions and postconditions. And in particular, when you're working with an untyped language such as Python, it is always a good idea to put in assertions as much as you can. Not in particular regarding types, because otherwise you may run into trouble here, but also if you have simple ways to check whether your result is correct or not, then please do so. When I say simple checks, this is actually a good question. If we think again about our function remove HTML markup, you remember this is the function which is supposed to take out arbitrary HTML markup from strings. Here, the question of what is the correct post condition is actually tricky, because specifying the post condition actually means that, well, what is the result of removing HTML markup? The result of removing HTML markup is, well, removing HTML markup. And in the absence, so the specification of what should be done is actually close to a second implementation of the whole thing. So if you have a second implementation, an independent implementation, then you can make use of this as a check. But then the question is, if you already have a second implementation which you use for a check, why bother building the first implementation at all? So why doing things twice? If you're in the aviation business, that's actually how they do things. They build things twice, and then they compare things against each other. And if there's a deviation, then There's some log message being printed out, some red light showing up in the cabin, and companies like Airbus or Boeing automatically notified that one of their software pieces just produced an invalid result. However, in here, well, in here, unless we have a second implementation, there's no good way for us to come up with a full-fledged post condition. However, we can do a simple partial check on our result. And an important partial check in here is, and that's very simple, we can make sure that the result no longer contains any HTML tags, which is an obvious condition. So after we have run any text through our remove HTML markup, then there should be no more markup in here. And that's something we can check. And this is actually a post condition which catches several of the errors that we have encountered before. Such such assertions also work. So, and by the way, this actually also works well as documentation for what remove HTML markup does. Namely, it removes any angle braces out of your angle brackets out of the string, meaning that, well, that's already close, a good approximation to removing all HTML tags. Likewise, here we have something, an obscure function, either x and y and z are equal, or the result is greater than the minimum, and the result is less than the maximum. This is an interesting question. Which function could that possibly be? And yes, well, what is the relationship in here? I will leave this up for you for the quiz. And all of these are simple ways for you to ensure that parts of your program work correctly. The neat thing about having such assertions also is, as it comes back to debugging, not only do they detect bugs quickly, but they also help you in locating defects quickly. Because if you have a function, and this function is being called, and this function's precondition is satisfied, and then the post condition is violated, well, where did the error occur? Obviously, in that very function whose precondition was satisfied and whose post condition was violated. So rather than having this long execution, you now know, well, there was this call, here everything was fine, here things were broken, this is where the error was, and then you can immediately jump to that function whose precondition was satisfied and whose post condition is violated. Ich habe diesen Titel nicht auf Apple Music gefunden. This is interesting. Fun. Okay, so let us finish with the most important or most useful, or most useful. Your mileage may vary, but maybe one of the most useful usages for assertions, and this cannot be overstated. So far we have seen how to check individual functions for whether they work well or not. But you can also use assertions to actually check complex data structures. And this is one of the biggest debugging helps you can ever have. I cannot stress this enough, how super useful this is. The idea is as follows. So you have a data structure. Well, over here I'm using a time class with fields, hours, minutes, and seconds. So far, so good. And the thing is, if any of this data gets corrupted, who knows? Seconds maybe, who knows? Maybe seconds is a value of 100, or maybe hours is negative, whatsoever, okay? You're not going to notice that until millions of cycles later, or maybe never, when somebody actually tries to do something with the corrupted data. And therefore, it's important to catch such errors at the very moment they occur. And the idea on how to do that is pretty trivial, but super effective. You insert a precondition or an assertion into the functions that actually set these data structures and check whether the arguments to set these data structures are actually okay. Or you can actually go one step further. You can introduce a special method or a special function that does nothing but checking whether the current data structure as it is okay. So this is conveniently called rep OK for OK representation. And this one simply checks whether the hours are valid, whether the minutes are valid, whether the seconds are valid. By the way, if you wonder why it can be that a minute has 61 seconds, this is actually because of leap seconds. Every once in a while, we have to introduce leap seconds in order to actually get the current time in line with the rotation with the rotation time of the Earth, such that years and days are still aligned as they should be. So, but as soon as you have such a method in here, which actually checks the current status, and you invoke this, say after any setter, for instance, then you can be sure that this data structure is always okay at all times. And you can be, one can be pretty, one can be pretty, pretty obsessed with that. Um, in particular, if you have very large data structures. Here's an example. This is a red-black tree. I don't know whether you have ever seen red-black trees. Red-black trees are among the most efficient search trees ever invented. So you can use them for databases, for search trees in memory, for whatever. In particular, they are always balanced. They're super fast as it comes to adding and deleting elements and whatnot. And they also are the most horrible data structure ever invented as it comes to debugging things. If you ever become a computer science professor and want to torture your students, please go and let them implement a red-black tree. In particular, since errors in implementation in red-black trees are not apparent immediately, they only become apparent after another dozen or 100 insert or delete operations, and that's when everything breaks down, and you can spend hours and hours, if not days, to debug a red-black tree. That is, unless you know how to do it. Because, see, what is a red-black tree? A red-black tree, we have a black node at the top, that is the root node, and every time, so this always comes in iteration. Black nodes have red children and red children have black children and so on. And all these properties of a red-black tree form an invariant. And this invariant is something that we can again check with one of these repo-k methods. So we can, for instance, say, I want to make sure that my root node never has a parent. Sounds obvious because the root node is defined as the root node, which has no parent, but in the implementation, your nodes may actually have parent pointers, and therefore you want to make sure that your root does not have a parent pointer that points somewhere. Otherwise, oh, disaster is going to occur. The root has to be black. Well, that's a very easy assertion. Red nodes have only black children, and vice versa. So you have to traverse the tree, and then you check if the node is red, yes, then the children should all be black. And if the node is black, then the children should all be red. There you go. Equal number of black nodes on subtrees. Well, not too difficult either. Count all the nodes on the left side, count all the nodes on the right side. Make sure that these subtrees have a similar number of nodes. Actually, if you do this recursively, that's a bit expensive. So you may actually want to do this iteratively and then compare from the bottom up. The tree has no cycles. Well, of course, has to be, because if the tree would have cycles, it would no longer be a tree. This is, of course, correct from a theoretical standpoint, but the problem is if your tree implementation has cycles somewhere in there, and you try to reverse the tree with cycles and cycles and cycles, you're going to end up in an endless loop, and boom, where did this ever come from? And parents are consistent. That is, if I am a node and I have a couple of kids and I ask these kids who are your parents, then these kids should actually answer, yes, it's all me. There you go. These are all, well, not too difficult to implement checkers. I mean, it's on the order of something between 5 and maybe 15 lines of code for each. And as a whole, this will do a lot. But you know, the thing is that once you have these, whatever function you apply on your red-black tree, you will immediately catch the error at the moment it's being introduced. And this is important because, well, at the moment they're being introduced, you can look this up on Wikipedia, red-black trees, and you will find that say in the insertion operation is 4 pages of code. Um, the delete operation is 5 pages of code. This is incredible. You've never seen anything like that. And there's all the chances in the world that you will get this wrong. Well, unless you copy the code from Wikipedia, I assume. And with a replica method, well, you still have the very same chances to get it wrong, but at least you will know. And you if you have such a replica method, and then you say fuzz your data structure with plenty of random insert, delete operations in arbitrary orders. So this is very easy to test. You can easily create a long list of insert operations and then a list of delete operations and then more of these. You just throw millions of these at your red tree. And if these replica methods work under all circumstances, this is such a relief. This gives you so much more confidence in your data structure. By the way, you can do similar things for file systems, you know that? So you can write a checker for a file system that will, well, if you do this for every single aspect of your entire file system, with every operation that's ever run on your file system, then your file system operations are going to be tremendously slowed down. But for standard operations such as, say, adding a file, deleting a file, adding a block to a file, you can do a couple of local checks whether the data structure, whether the data structure of your file system, the structure of your file system is still fine. And again, this is going to find thousands and thousands of errors before they can propagate and create havoc. This chapter closes with a nice extra chapter for those of you who do not program in Python, but in a more system language like C. This would be a perfect moment for a raise of hands. Whoever programs in C or C++ or whatever. The main thing in C is, the real fun in C is that you are in control of everything. This includes memory, and which unfortunately also means that you are responsible for memory management. Sure, if you want to write an operating system kernel, then it's great to be in charge of more memory management because, well, that's the point of an operating system. But if you write application programs in C or C++, well, prepare to spend some extra time on handling memory, and in particular to debug memory issues. So in particular, in a language like Python, if you, for instance, access an invalid array element, say like this one, what you're going to get is a string index out of range because this is all checked. In C, however, here we go. I just wrote a program here which does the same. So it builds a string and then it returns an element out of that string. This is the same thing. This, in principle, should actually result in an error. Unfortunately, that's not how this works in C and C++. What you're going to get is undefined behavior. Undefined behavior is a very fun term in C. This simply means that anything can happen. The program may crash. The program may do nothing. The program, for whatever reason, may start drawing pink elephants on your screen, deleting your hard drive, or sending out your private files into the world. This is all legal C behavior covered by the specification. Just saying. It would be a rare thing for this to happen, but if you build a C compiler that actually does this, oh, it's undefined behavior. Finally, we can do whatever we want with the user's program. Now, it is covered by the C specification. So in our case, what happens is simply nothing. And simply nothing is, of course, a bad thing because you will have no idea that your program just entered undefined territory and that something really weird has happened behind the scenes, and that from now on your program can fail in any possible way on any possible system whatsoever. And herein we built a small C memory simulator, which is a bit of fun, in which we can actually simulate what's going on behind the scenes, where we can build some memory and work with that. But the really fun thing which I want to highlight here is not so much how these C functions work, but rather how we can catch such errors. And this is really neat. And this is something that has come up in the last years, there's a couple of ways, a couple of new tools that have come up which allow you to automatically check whether and how your C programs works with memory and whether it accesses memory in specified and legal ways, and if not, how to report these things. Um, I'm actually building here such a system for you to show how these things work. The main idea is that for every piece of memory you record, whether this byte was ever allocated and whether it ever was initialized. If you try to access any byte that is not allocated, then you get an error. And initializing simply means, has it been written before it's being read? Because if it has not been written by your program before it's being read, this simply means that you're reading some memory which is uninitialized, which again can have arbitrary consequences. And by setting up either your runtime system or the C compiler to actually track such allocation bytes and such initialized bytes, this allows you to automate. This allows the program at runtime to track whether your memory accesses are sane. There are two major tools that you can use for that purpose. Again, if you program in C, C++, if you program in Python, memory, what is memory? You just rely on Python to do the right thing and you don't worry about it. Whoops, there you go. You just run around in your dreamland, never worrying about anything that happens at the system level. However, if you work in C, if you're a real programmer, you want to go down to the core, you want to know every bit personally, and you want to control it, and you want to make sure that your program never ever uses any more memory than it could possibly need. That's when you can make mistakes, and that's when you need these tools which are called sanitizers. And these sanitizers exactly manage the memory by putting in these extra bits. And there's two of these which are extremely popular. One is Valgrind. A Valgrind is a tool that is actually an interpreter for x86 executables. You can take an x86 executable and run it through Valgrind. And then the Valgrind tool will read each opcode of the x86 program and automatically execute it. And while it's interpreting your x86 code, it can just as well manage memory while it's doing that. And that's actually something it does by default. Actually, an x86 Valgrind interpreter could be a neat thing if you have an ARM machine, say one of these new Macs, for instance, and you want to run an x86 program on that, you could actually do this via Valgrind. That's true. Apple comes with their own interpreters, which are way better than that. But Valgrind can take any program. It can even take whatever, your favorite Microsoft Office suite whatsoever. So even if you have a third-party program or a third-party library, for which you don't have the source code, you can still run this through Valgrind. And remember this access here, which in this case is an access of uninitialized memory. You run this through Valgrind, and oops, what is this? Just use after free. Oh, okay. How is it possible that this worked yesterday and today doesn't? I fear. No, actually, I have set up a new Valgrind version. What is going on here? It worked yesterday, but it didn't. But it doesn't work today. No. Okay, good. Let's keep it like this. Valgrind normally should run automatically and automatically figure out that your program doesn't work as it should. What is the loop system? Okay, I'm going to check this out. The available chapter still has the right thing. Okay, probably me upgrading my Mac to the newest operating system version. That's probably what's going on here. See, I should have checked that. If you go to the binder version on Linux, there I have made sure that Valgrind is there and Valgrind works as it should. Second thing here, let's hope that this one works, is checking memory usage with the memory sanitizer. In contrast to Valgrind, which is an interpreter of x86 code, a memory sanitizer is a device that is built into a compiler. So you compile your program with a memory sanitizer enabled. So that's this extra function here, fsanitize equals address. This enables the memory sanitizer. And then at a runtime, the program itself will make sure, will automatically keep track of all managed memory. So its memory usage, again, is going to increase because of all these extra bits required for initialized and allocated memory. And if you do that, you just compile the program, then you run it. And in contrast to Valgrind, where the program can be slowed down by a factor of 10 to 100, depending on which checks you run. If you do this with a memory sanitizer that is built into the compiler, the extra overhead is much smaller. We're talking about 70%. That is, instead of taking 100 seconds, your program is going to take 170 seconds. So even an interactive program would still be very usable with that. And if you do that, what you're going to find out if your program then violates any memory assumption, then you're going to get this wonderful error message, which tells you that your function has just tried to access some memory which wasn't there. And you can even integrate this with your favorite command line debugger to immediately jump into the debugger at the moment the program fails. And you're going to get error messages whenever your C program fails. There's a very important lesson for you, and this is probably one of the most important ones. If you program in C or C++, run your program through memory sanitizers at all times. If you don't do this, you're going to miss out so many dangerous bugs. You do this, it's really a minor extra overhead, and it catches so many bugs that are otherwise so hard to find. This is like a big assertion running at all times over your memory in the background, with catching all the bugs for you, which otherwise for you as a human would take hours, days, or possibly even weeks to find. So this is an important lesson for all of you who work at the system level. So a couple of recommendations at the very end. Assertions can check things, but you should not rely on assertions being on, meaning that if you have conditions on third-party input which need to be checked, say the inputs should not contain any quotes or likewise, then you should obviously go and not do this via assertions, but actually via checks that are baked into production code, such that your code still does the right thing even when assertions are turned off. And also, if there are assertions which are rather cheap, such as verifying the square root results, for instance, then consider leaving these on, and you're going to check a number of extra errors, even in production code, before these errors propagate too far. So this is what we're having for assertions. We've seen preconditions and postconditions and invariants. The more assertions you have, the earlier errors are detected, the easier it is to locate defects, and the better the guidance to failure causes towards debugging. So this is what we're having about assertions. And have fun reading the chapters and go through the individual examples. And I'll make sure I'm going to have a new Valgrind version running on my machine, such that this will also be reflected again in the chapter. Thank you very much, and I am happy to take questions regarding the chapter.